Assalamu alaikum. Welcome to the next lecture. So, in this lecture, I'll start first from the sub-synchronous resonance. In the previous lecture, I just told you to remember this uh, concept, and I will explain it in the next class. So, I'll first start from the sub-synchronous resonance, and in short form, it is also known as SSR. Electric power generation involves interaction between the electrical and mechanical energies which are coupled through the generators. This also we know that. It follows that any change in the electrical power system results in the corresponding reaction response, or we can say change in the mechanical system and vice versa. Such type of things that we discuss, that the reaction between the electrical and mechanical system we discuss in the stability analysis also, which are very critical in understanding the stability concept. Now the loads are slow changing. They translate into the slow changing mechanical torque on the rotor shaft, which in turn is matched by slow changing rotor angles to new steady state angles by the rotor and the stator, along with the adjustment in the mechanical power input to the rotors through the turbine. Actually, this has also been covered in the stability analysis. In that case, when the slow changing loads were considered, we said that is the steady state stability. So major disturbances such as faults and fault clearing etc. result in the high transient torques on the mechanical system and corresponding transient twisting of the rotor shaft couplings between tandem turbine and generators. So whenever a major disturbance such as a fault occurs, it results in the high transient torques on the mechanical system. So this also has been covered in this transient stability analysis. Now, an important thing that we need to remember and that we need to understand, a large turbine generator unit acts as a whole mass, has its resonant frequency below about 5 Hz. We can say it may be around 3 to 5 Hz with other nearby large turbine generators. So they may resonate at other large turbine generators with this frequency. So this is actually mechanical frequency. This is not the electrical frequency. A cluster of the turbine generators closely coupled in a region representing a large collective rotating mass would have a resonant frequency in the range of 0.2 to 3 Hz. So when the large number of turbo generators are taken into consideration, we can represent them as collective rotating mass. Their resonance frequency has a range of 0.2 to 3 Hz. Now, coming to the SSR phenomena, it is actually a phenomena in which the resonant frequency of the electrical system. So, the resonant frequency, that is actually the frequency that occurs between the capacitance in this capacitance of the network and the inductance of the network. They have their own electrical frequency. If that frequency matches with the coincides with the we can say mechanical resonant frequency, that is with the resonant frequency of the turbine generator shaft that we have just considered to be equal to 0.2 to 3 Hz, in such a manner that there is a continuous exchange of energy between the mechanical shaft of the turbine generator shaft and the electrical system. So there will be the exchange of electrical energy. So what this exchange of energy will do? This exchange of energy causes torsional stress on the turbine generator shaft. So it will result in the stress, that is the torsion that is rotating stress in the shaft, that can lead to severe damage such as cracks in the turbine generator shaft. So it will result in the crack, and in some severe case it may wholly damage or fracture the shaft. This actually has been witnessed in some of the turbo generator generating station where the turbine, or we can say the shaft, have been fractured, damaged by this sub-synchronous resonance. So in that case, the mechanical resonance coincides with the electrical resonance, and it results in the damage of the shaft. This happens, I don't remember this, but I will let you know in the next class, but it happens in 1978, and it occurs twice in that generator. So this phenomena, that is the sub-synchronous resonance SSR, will occur only in the presence of series capacitor. As we know that when there is a series capacitor, there will be some resonance between this series capacitor and the inductance of the line. So the resonant frequency of these two electrical elements, that is the capacitance and this inductance, will be given by this. Let us denote it by Fe, that is equal to 1 by 2 pi into 1 by root of Lc, where L is the inductance of the line, C is the series capacitor that we have been installing in the line. So let's multiply it by omega and divide by omega and take this omega inside this square root. So when it is taken inside the square root, it will be omega square. One omega will be multiplied to L, another omega will be multiplied to C. It will be omega L into omega C. This omega C will be equal to 1 by xc. Xc will come to the numerator. It will be equal to xc by xl square root. So this omega will be equal to 2 pi f naught, where f naught is the system frequency, that is 50 hertz in our case, because omega L, that is 2 pi f naught into L, that is the reactance at the power frequency, that is this f naught. So this resonant frequency will be equal to f naught into square root of xc by xl, and we know that this xc is usually kept less than this xl. So, or xc by xl, which is the degree of series compensation factor, it is value is usually kept 0.3 to 0.75, and you will see that when this is the case, this resonant frequency will be lower as compared to the system frequency, which is 50 hertz. So if this xc by xl is such that this resonant frequency comes close to the resonant frequency of the turbine generator set, that is around this, it will result in the exchange of energy, and which will result the actual fracture of the we can say the shaft. So we need to actually see this type of the thing that will happen. So we need to keep this value slightly higher as compared to the value which will match it to the frequency of the mechanical system, resonant frequency of the mechanical system. So this is what is known as sub-synchronous frequency. Sub-synchronous frequency means the the component of the frequency which is less than the actual frequency. That's why it is known as sub-synchronous frequency. Now let's come to the another series compensator, that is known as static synchronous series compensator. So it is actually a dual of the statcom, while statcom is used in parallel with the statcom is usually used in parallel with the transmission line, but this static synchronous series compensator is used in series with the transmission line. So as I have told you that this is actually nothing but the dual of the statcom. So this is how it is connected. This is the transmission line. So this is the coupling transformer, and we have the voltage source converter. And in earlier case, this transformer was not connected in series with the line. You will see that it was connected, its output was connected directly to the transmission. It was the statcom was connected parallel to the transmission line between the line and the ground, but this is connected in series with the transmission line. So here it shows that it is capable of exchanging the real and reactive power. For real power, it should have some energy source present, and there is a control, that is P reference and Q reference, or we can say R reference and X reference, and based on them it can do the control, or we can say it can control the value of P and Q, whether it is drawing P and Q or supplying P and Q. So the basic operating principle of the SSC can be explained with reference to the conventional series capacitor compensation of figure first, that is this one. We'll first discuss it. We have already actually discussed this, so we'll first again introduce the same circuit to you before going into the actual SSSC, that is static synchronous series compensator. So in this case, The phasor diagram clearly shows that at a given line current, the voltage across the series capacitor forces the opposite polarity voltage across the series line to increase by a magnitude of the capacitor voltage. This is an important sentence. You can see that in absence of this VC voltage, you will see that the voltage across the inductance was only this much. That is from this point to this point. Now, because the presence of this voltage, you can see that this voltage and this voltage remain the same. Let us say the reactance will decrease, the current will increase, the voltage across this will be now greater as compared to without this XC, because the net reactance has increased, the voltage difference remains the same. So as net reactance decrease, current will increase, the voltage drop across will increase. Now what will happen to this voltage? Now the total voltage drop will be equal to this voltage drop plus this voltage drop. Since this voltage drop is opposite to the voltage drop of this, that means the net voltage will again be equal to the same, because this will remain the same, but the voltage across this will increase by an amount which is equal to the VC, so that their summation will remain again the same. That is what is meant by this sentence. Thus, the series capacitive compensation works by increasing the voltage across the impedance. So in this case, voltage across the impedance increases of the given physical line, which in turn increases the corresponding line current and the transmitted power. So when the voltage increases, actually it increases the current. When the current increases, transmitted power will also increase. While it may be convenient to consider series capacitive compensation as a means of reducing the line impedance, definitely ultimately we are actually the basic concept, we start from the same thing, that actually we are reducing the line impedance. In reality, as explained just above, it is really a means of increasing the voltage across given impedance of the physical line. So even if we know that it is the reactance that actually has decreased, but in other words, we can say that it is the voltage that has increased across this impedance that makes this current to increase, and ultimately power increases. It follows therefore the same steady-state power transmission can be established if the series compensation is provided by the synchronous AC voltage source. Now, if we have some voltage source which can be inserted in series with a line, and that voltage source is capable of increasing the line voltage by the same amount as shown in the figure 2, you can see over here we are inserting a voltage source in series. That's why here this SSSC is connected in series with the line. This is the line, the primary of the transformer is connected in series with the line in case of SSSC, but in case of STATCOM, the primary will be connected parallel with the transmission line. So that is the difference. So when it's connected in series with the line, it means we are actually injecting a voltage source in series with the line, but we will try to inject the voltage in series with the line which has the same sort of the effect. That means which will try to increase this voltage, and ultimately it will be in this direction. So what I mean to say is that the effect of the capacitor that is here, this voltage source will have the same effect as if the capacitance was here. So how will it do this? It's provided by synchronous as whose output precisely matches the voltage of the series capacitor. So its output should be in such a way so that its voltage should be again in phase opposition to the voltage across this. So this will happen only when its voltage will be equal to VQ is equal to VC, that is equal to minus J XC into I, that is equal to minus J K X into I, where K is the degree of series compensation, which is equal to XC by X. So XC can be replaced by K into X. Now this voltage source has to be in such a way so that this voltage lags the current by 90 degrees for the system to be similar to that of this. That means this voltage should be lagging so that current will be leading. That means it has a capacitive effect. So VQ will be inserted like this, plus J VQI by I or minus J VQI. This is the magnitude of this voltage. So I is the phasor, that is the current, divided by I, it will be only introducing the angle. This we have done for the STATCOM also. where we introduce the angle of the voltage to the current of IQ. Here we have VQ. So this angle will be multiplied to this magnitude, and then if we have to use it as a capacitor, then we have to multiply it with minus G. So VQ, if it is minus G, this VQ, this I divided by I, that means uh, this voltage will be leading to this current, sorry, lagging to this current. If it is minus G by 90 degree, it will act as a capacitor. So you will see that here we have the power V square XL minus XC. So it will be equal to V square VQ by I. It has the effect of XC sine of delta. So this will be similar to that of this. Now, thus by making the output voltage of synchronous voltage source as a function of line current as specified in the above equation, the same compensation as provided by the series capacitor is accomplished. However, in contrast to the real series capacitor, the synchronous voltage source is able to maintain the constant compensating voltage in the presence of variable line current, or control the amplitude of an injected compensated voltage independent of the amplitude of the line current. This is the main advantage of the SVS, because in earlier case this amplitude of the injected voltage was a function of the current, because impedance in that case was constant. For a normal capacitor compensation, the output voltage lags the line current by 90 degrees. I have just told you. For SVS, the output voltage can be reversed by a simple control action to make it lead or lag the line current by 90 degrees. That means if this voltage leads to the current by 90 degrees, it will act as a capacitor. If this voltage if this voltage lags to the current by 90 degrees, it will act as a capacitor. If this voltage leads to the current by 90 degrees, it will act as an inductor. So in this case, the injected voltage decreases the voltage across the inductor line impedance, and thus the series compensation has the same effect as if the reactive line impedance was increased. So if it is injected in such a way that we are using here plus, so in that case it will act as it will introduce the effect of the inductance. We can say it is as if we are increasing the line impedance. With the above observation, a generalized expression for the line injected VQ can be simplified and written like this: VQ is equal to plus minus J VQ zeta I divided by I. I is the phasor, I is the magnitude of this, VQ is the magnitude of the VQ. So we can say this term will have the angle of this I, and if we use plus J, it will act as a, we can say, leading to the current. This will add the leading to the current by 90 degrees. If we as minus 8, this will be lagging to the current by 90. Plus, if we use the plus J, that means it will act as it will introduce the inductive effect. If we use the minus J, it will use the capacitive effect. So in this case, this VQ can act as inductor. If we use here plus, in that case, this VQ will be leading to this current by 90 degrees. So it will be an inductive effect. If we are using minus, it will introduce the capacitive effect. For this equation, where VQ zeta is the magnitude of the injected compensated voltage, and this changes from 0 to VQ max, there will be some maximum voltage, and zeta is a control parameter because it will be changed to change the value of the VQ. The series reactive compensation scheme using a switching power converter voltage source converter as a synchronous voltage source to produce the controllable voltage in quadrature with the line current as defined by the above equation, whether it's plus or minus, is as per IEEE and CIGRE definition termed as static synchronous series compensator. So in this case, it is also doing the same thing as was done by the we can say synchronous machine, because without having the actual inductor and capacitor, that it was producing the effect of this inductor capacitor. It is static because there are no rotating parts, that's why it is static. It is connected in series, that's why it is known as static synchronous series compensator. Now Let us see what will be the transmitted power versus transmission angle characteristics. This is the same triple SC, which is injecting a voltage in series with the line, and it is using this minus at this point, at VQ is equal to minus JVQ I divided by I. I is the phasor, I is the magnitude of this phasor. So in that case, looking at this phasor, you will see that this VL minus VQ will be this voltage, and divided by 2, it's half, will be the sine component of this voltage VR, where Vs is equal to VR is equal to V. That means VR sine of delta by 2, or V sine of delta by 2, is equal to VL minus VQ divided by 2. That is what this equation means. And we know that VL will be equal to I into X, that is the line reactance. This X is actually equal to XL. That means it will be equal to Ix minus VQ divided by 2 is equal to V sine of delta by 2. So this current I will be equal to twice V sine of delta by 2 plus VQ divided by this X. That is twice V sine delta by 2 plus VQ divided by X. Now the power that is transferred to this will be equal to V I. I will be definitely in this direction, which will be perpendicular to this voltage and to this voltage, and the angle between I and this VR will be delta by 2, as we have already discussed this. That is why I have not shown that here again. So V and I, power will be equal to this V, this I over here, an angle between the delta by 2, cos of delta by 2. So we have to replace I by this. When you multiply this equation by V cos of delta by 2, we will get power. So this will be equal to twice V square sine delta by 2 cos delta by 2 divided by X. So combining twice sine delta by 2 cos delta by 2, it will be equal to V square by X sine of delta, plus, so it will be multiplied by V into cos of delta by 2 divided by X. So it will be multiplied by V into cos delta by 2. So this equation will be then equal to V by X VQ cos of delta by 2. This is the total equation of the real power transferred from sending end to receiving end. So there will be the enhancement of the power. Apart from this, you can see this much will be the enhancement of power, and it will be independent of delta, because even if delta is equal to 0, this term may vanish, but this term will remain as it will make it equal to V into VQ divided by X. So the normalized power P versus angle plots as a parametric function of VQ are shown in the figure. This is the normalized power. This is when VQ is equal to 0, and then when we change this P versus this delta, this will be normal curve. So this is VQ is equal to 0.353. So in that case, this will be the curve. So at angle delta is equal to 0, there will be some power transferred, even if the angle between receiving end voltage and sending end voltage is 0. So here VQ are taken as 0, that is for this case, plus minus 0.353, that is, this is for plus 0.353, and this is minus 0.353. That means in this range it will act as inductive, and in this range it will act as capacitive. So this plus minus, this plus or this minus is not with respect to this equation, that is this equation. So since we have assumed in the derivation this is minus, this is in this direction, that means we are here using minus. So taking this into consideration, when this equation is derived, we are getting it. Now we are taking this to be positive. That means plus 353 will be this plus 3. That means its minus would have been already taken. That is why I told you that plus 0.353 here will be in the capacitive mode. And it is in the capacitive mode that power will be increased. For the comparison purpose, the normalized power P versus angle delta plot of the series capacitor compensator two machine system are shown in the figure below. That is this figure. This will be the series capacitor series compensation. For k is equal to 0, k is equal to 1 by 5, k is equal to 1 by 3. So these are deliberately kept as 1 by 5 or 1 by 3, so that this will be equal to 1.5 maximum power. Here maximum power will be equal to 1.25. Same is the case with here. This will be 1, this is 1.5, this is 1.25, this is 1.5. This is 0.75 and this is 0.5. So these three curves are actually compared with this because their maximums are same. For the comparison purpose, K is chosen to give the same maximum power as SSSC with corresponding VQ. That is, at delta is equal to 90, K is equal to 1 by 5 and VQ is equal to 0.353. If that is the case, you will see maximum power will remain the same. So when K is equal to 1 by 3 and VQ is equal to 0.757, this will be per unit, definitely, this one. This will be unitless. So we'll get the same value of power, that is 1.25. Comparison of the corresponding plots in these two figures clearly show that the series capacitor increases the transmitted power by a fixed percentage of that of transmitted by an uncompensated line at a given delta. What does this mean? That means, let us say for this case it is increasing this power from this point to this point by a fixed percentage. That means 0.25 of the maximum power, because this is equal to 1.25 at every case. And when delta is equal to 0, 0.25 of the 0 will be again equal to 0. It will not increase any power in that case. But in case of SSSC, it increases the power by a fixed fraction of a maximum power transmittable by the incompensated line. So in case of this, it will increase it by a fixed fraction, not fixed percentage, because it will always be added to this percentage. It will not be multiplied by that percentage. So that means when delta is equal to 0, it is capable of still supplying some power. That is the main difference. And one more thing, that means this power will be supplied to this independent delta, but this will be still dependent upon the delta, because when delta is equal to 0, it is capable of supplying some real power. And in the important range of this in this, that is between 0 and pi by 2, because this is an important range, and during the steady state you will see that most of the time that our power system will operate in this range only, not in this range. So that is one more importance. For application requiring steady state or dynamic power flow control, the basic P and delta characters shown in the figure indicate that SSSC, similarly to the STATCOM, inherently has twice as wide control compensation range as VA rating of the converter. For example, if VA rating of the converter is, let us say, 1 per unit, its control range will be 2 per unit, because it will go 1 per unit in this range, capacitive range, and 1 per unit in this inductive range. This means that the SSC can decrease as well as increase the power flow to the same degree simply by reversing the polarity of the injected AC voltage. So that means if we keep this plus, so we have one voltage range. If this keep this as a minus, we have another voltage range. So this is one more advantage. Now the VI characteristics of SVC, SSSC is similar to that of the STATCOM. Only thing is that now the voltage and current will change the can say the axis. So here, for any amount of current, you will see this is actually the ideal VI characteristics and ideal impedance characteristics of the SSSC. So for any amount of current, it will always inject a constant voltage VQ, which will be equal to VL max. So again, this will be done by the control by the proper switching of the converter. So it will always try to inject the same voltage in the inductive mode or in the capacitive mode, irrespective of the current. Definitely, this current that is flowing through this will be limited by the Imax, because it will be the current rating of this. And this is the impedance control. So in case of TCSC, we have actually the same sort of the control. In this case, we have some impedance limit from this point to this point, otherwise the voltage control would have been same because of that resonance. So to avoid that resonance, we have to actually avoid that range, that is alpha L minimum to alpha C minimum. So this will be alpha M minimum. In that case, in this region it will be like this. So for this region it will be like this, maximum capacitance, this will be minimum capacitance like this, and this will be voltage control. So for this case, again, this will be impedance control. There will be no discontinuity in this region. Here also there will be no discontinuity. The SSSC can provide capacitive or inductive compensating voltage independent of line current up to its specified current rating. So it will inject a voltage at maximum voltage independent of the line current up to the maximum value of the current. Thus, in voltage compensation mode, the SSSC can maintain the rated capacitive or inductive compensating voltage in the face of changing line current theoretically in the total operating range from 0 to IQ max, as illustrated in the figure that I have shown. The VA rating of SSSC is simply the product of this Imax and VQ max. In impedance compensation mode, the SSC is established to maintain the maximum rated capacitive or compensating reactance at any line current up to the rated maximum value. So as shown by this graph. So it maintains here the value of the maximum reactance with respect to the line current. So in that case it will be for inductive region and this will be for the capacitive region. It is seen from the figure above that the SSC of 1 per unit rating, VA rating covers a control range of 2 per unit compensating hours. That is, the control range is continuous from -1 per unit for capacitive hours to +1 per unit to inductive hours. So that can be seen from this. This will be equal to VC max into I max. This will be -1 per unit. This will be VL max into IL max. I max will be equal to +1 per unit. Total will be 2 per unit from here to here. In many applications, almost in every case, only capacitive series line compensation is required. This inductive series line compensation is required in case of faults only to limit the fault current. Now the comparison of TCSC and or TSSC and SSSC. So the SSSC is a voltage source type and the TSSC and this are variable impedance type series compensators. Although both types of compensators can provide highly effective power flow control, their operating characteristics and compensation features are or can be made different. The SSSC is capable of inherently generating a controllable compensating voltage, that's VQ, over an identical capacitive and inductive range independent of the magnitude of line current. This is not in case of this TCSC. The SSSC has an inherent ability to interfere with the external DC power supply to provide the compensation for the line resistance by the injection of real power as well as for the reactance by the injection of the reactive power, for the purpose of keeping the effective X by R ratio high, independent of the degrees of series compensation. The variable impedance type series compensation cannot exchange the real power except for the circuit losses. With the transmission line, they can only provide the reactive power compensation. So in SSSC, this real power exchange is only possible when there is an energy source provided at the input of the DC side. You can see it from here. I have shown it in the first energy source. This is optional. This is only the case when we require the real power exchange. The SSSC with an energy source or sink increase the effectiveness power oscillation damping by modulating a series reactive compensation to increase or decrease the transmitted power and by concurrently injecting an alternating virtual positive or negative real impedance to absorb and supply real power from the line in sympathy with the prevalent machine swings. As we know that this dampings can be increased by actually injecting the actual electrical power. This damping, or we can say when we know that there is a change in the electrical power, there is a fall, there is a change in the load, the new steady state for the rotor has to be established, and the new steady state will be established after having some oscillations about this steady state point. When you supply some electrical power and when you before actually it settling to the new steady state, these oscillations will be damped. So when this SSSC has energy source and it supplies the electrical power in that case, so it will try to damp these oscillations. Also when sometimes mechanical power may reduce, so in that case again the new steady state delta has to reduce. New steady state will again be attained by, but before going through some oscillations. So in that case, it will absorb some power by charging some battery or something else, or it will deviate the power flow. So in that case, when it absorbs some power, electrical power, uh, so in that case also we can say that or it supplies in that case electrical power. So the load from the that has to be come from the generator is relieved. So when that has relieved, the difference between the electrical power and mechanical power will be reduced. Again, the oscillation will be damped. The TCSC and TSSC employ conventional thyristors with no internal turn-off capability. These thyristors are the most rugged power semiconductors available with the highest current rating and voltage rating, and they also have the highest surge current capability. Actually, this is the advantage of these thyristors, or we can say the series compensators employing thyristors. For short term, they are suitable to provide bypass operation to protect the associated capacitor during the faults because their rating is very high. The SSSC use GTO, that is gate turn off thyristors, that's fully controlled thyristors. These devices presently have lower voltage and current rating and considerably lower short-term surge current rating. These are suitable for short-term bypass operation only if anticipated line fault current is relatively low. So for this case, if the fault current is high because of their higher current current capacity, they will be used for you can say they will be used for the short-term bypassing. Therefore, they may need external fast protection during severe line faults by an auxiliary conventional thyristor bypass switch. So they need conventional thyristor bypass switch to have some bypass due to this or bypass provision. RMO, metal oxide varistor, that this is used to we can say arrest the high voltage across this GTO, or by some other means suitable speed. Not all the series compensator would also typically have a mechanical bypass switch for backup. But sometimes if it has a mechanical switch, that would be good, but in most of the cases they have to be used the thyristor as a bypass switch. So this is actually the advantage of TCSC and TSSC over SSSC. Now the variable impedance type compensator, that is TSSC and the TCSC, are coupled directly to the transmission line and therefore are installed on high voltage platform because they are connected in series. Therefore we cannot have a transformer so that we can step the voltage down and then connect them. The cooling system and the control are located on the ground with high voltage insulation. So the cooling system and the control has to be done with the high voltage insulation. So the SSSC requires a coupling transformer rated for 0.5 per unit of the total series VA compensating range, because for 1 per unit this only requires 0.5 per unit, and the DC storage capacitor we need. However, it is installed in a building at ground potential, at very low potential, and operated at a very low voltage, typically at below 20 kV. Thus, this installation needs only relatively low voltage insulation for a cooling system and a controlling interface. This is one more advantage of this. So these are the different points which actually clearly determine the differences between the this SSSC and TCSC. And similarly, we know they provide the series compensation. I hope you understood. I will stop over here. Thank you.